What we have in front of us right now is this classic problem where they start us with a velocity. It's sort of telling us how quickly we're moving. And they want us to kind of find two answers out of this. They want us to find an answer that is our displacement. So, how far from our original position are we? And then the other part of it is they actually want to know what was our full distance that we traveled. And these are two different things, remember. So, what I always tell people, kind of the way I keep track of it in my head, is displacement means, let's say I start here at 0 and I take 5 steps forward, but then I go ahead and I take 3 steps backwards. Well, then my displacement here, how far I moved from that original position, that's just 2 units. 2 steps is all I ended up going. However, if we talk distance traveled, if I want to know how many steps did I actually take, well, I took 5 steps to get out this direction, and then I took 3 steps back. So in the end, I took a total of 8 steps. So displacement wise, I moved only 2 steps, but it took me 8 total steps of traveling to get to that place. And so those are slightly different animals when we come to doing these types of problems. So we'll start with displacement. Displacement is kind of the easy one. Displacement allows us to take our positives and our negatives and add them all up. And so when you're doing displacement, displacement is just your standard antiderivative. It's a standard definite integral process because definite integrals add positive and negative areas to end up giving you out what that net change is. So that's what we'll do for part A here. Part A is kind of the quick and easy one you get for free because you should know pretty well how to do a definite integral at this point. So to find out how far from our starting position we moved, our displacement, we would take the antiderivative from 0 to 10 because that's the amount of time that we're working with here. And then we would just go through our normal definite integral process. So we start by doing our power rule. We're going to add 1 to the power and then divide by that new power. Then minus 10, there's an unwritten 1 on that t, so we add 1 to the power, divide by the new power, and then numbers by themselves gain a letter back, so that 21 gets a t. And because we are doing a definite integral, we now get this evaluated from t equals 0 to t equals 10 here. And this is when we do what I just referred to as the top minus bottom method. We are going to take the top value, plug it into this equation, and then we are going to subtract off the bottom value plugged into that equation. And so out of there, what that would look like is we get 10 to the third over 3 minus 10 times 10 squared over 2 plus 21 times 10. That's the top value plugged in. And then we subtract off that bottom value plugged in. So plugging in 0 everywhere I see. So minus 10, 0 squared over 2 plus 21 times 0. And then we toss all that into your calculator, and out of there you're going to see that your net displacement, how far you moved from your starting position, was 130 over 3 meters. So that's saying that over that time interval from 0 to 10, you might have moved forward, you might have moved backward, but your displacement from your starting position was only 130 over 3 meters. Now we come in and we do the one that's a little bit more tricky. It's not horrible, it's just we have to now consider that we were taking steps forward and backwards potentially. And so what that means for our total distance traveled is we're going to have to figure out where did our velocity change. So remember that if you're doing positive velocity means you're moving forward. Whereas negative velocity would mean you're moving backward. And then adding the forwards and the backwards all up, that's what gave us our displacement. However, on this one, we want to know basically how much total movement did we do. So the movement points are going to change when our velocity equals 0, because that's when we stopped and we could or could not have changed direction. So the best way to handle this is to come through and you say, okay, well, I need to know when does my velocity equal 0. So we go back, we grab that velocity equation, and we're going to see when those moments of moving forward or backward could have happened. So we take that and we set that equal to 0. Anytime we got a squared power, a 2 or greater on our problem, you know that factoring is going to be what you need to do. So we have this set equal to 0, and now we need to factor this apart. So we're looking at a t and a t. We need two numbers that multiply together to give us 21 and then add to give us a negative 10. So going through that, you'd end up with negative 3 and negative 7. And so this allows us to see. We then break it into two smaller bite-sized problems. So whenever t minus 3 equals 0, that's when we were stopped. And whenever t minus 7 equals 0, that's also when we were stopped. So then from there, you just kind of do a little bit more algebra. You add your 3, and you end up with t equals 3. You add your 7 and add your 7, so you end up with t equals 7. So if we think about this now in terms of a number line, right? So we were starting at 0, ending at 10. So those are going to be our end points on our interval here. And then what we just discovered was that at 3 and then again at 7, we stopped for a moment. And so our direction could have changed in those moments. And so what you want to do now is you basically have to split this up into 3 little smaller integrals based upon those little subsets there. So what we're going to end up with here is we're going to end up, for this section, we would do the integral from 0 to 3 of our velocity equation. So of the t squared minus 10t plus 21 dt. Then we're going to add to that. Remember, as we do this, we can do these, and all we want to make sure we do is in the end, oops, that's not 0 to 3. This next one would be from 3 to 7 of that, t squared minus 10t plus 21 dt. And then on the last one here, we would add in the integral from 7 to 10 of t squared minus 10t plus 21 dt. The key on this is just knowing that all of this area that we get out here is got to be treated as positive area. So if we get out a negative value for our antiderivative, then we just need to make that positive. A lot of times, they kind of put in this extra notation. I think it's sort of unnecessary. They would sort of put these absolute value bars around this to let you know that whatever value you get out of there, you need to make that value positive. The great news about this problem is we've already done the antiderivative. We did that originally back on part A. It's all still the same antiderivative. So we're going to get t to the third over 3 minus 10t squared over 2 plus 21t. And then on this first one, evaluated from t equals 0 to t equals 3. Then we'll add to that. Oh, we already did the integral. We know what that is. That's again just going to be t cubed minus 10t squared over 2 plus 21t, and then evaluated from t equals 3 to t equals 7, and then we're going to add to that the same thing. So again, we get t to the third over 3, oops, I forgot my over 3 on this first one, minus 10t squared over 2 plus 21t, and then evaluated on this last one from t equals 7 to t equals 10. So again, you're just going to come through and play the top minus bottom game as you go through all of these. So you're going to take that top value, plug it in, and subtract off the bottom value plugged in. When we do that for this first one here, what we're going to get out of this, after we do all that work, is we're going to get out a positive 27 meters. When we go to do the second piece here from 3 to 7, out of that, we would end up getting out negative 32 over 3 meters. But what do we do with that? We turn that positive, right? We want that absolute value. So really, because we're just looking at total distance, so then that would be positive 32 over 3. And then on the last piece here, if you popped all that in and did it, you would end up going another 27 meters. So in the end, the total amount of travel that you did, you got to treat everybody positive. You're going to add 27 to a positive 32 over 3, and then add that to 27 again. And in the end, after you do all of that adding together, you will see that you traveled a total distance of 194 over 3 meters. So the big difference between displacement and distance travel, displacement, always just your standard, set the thing up 0 to 10, however far your interval is, and your result will be the net displacement, how far you moved off of your original position. And then the more tricky one comes when they want to know the distance traveled. And in that situation, you got to break up your integral based upon those moments when you would hit a zero velocity. And so that really makes it a whole bunch of little mini problems in one. The great news is you'll always kind of have your antiderivative done for you. It's the same antiderivative. And then we just make sure that all the values that we get out, whenever they're negative, we make sure we turn them positive and then add up the results from all of those intervals, and that's going to give us how much total distance we traveled to actually get a net displacement of 130 meters. Thanks for watching my video. If you liked it, please click that like button and subscribe. And also share it with your friends and anyone else you know who might be crying about an upcoming AP Calc test. You can find more videos from me, more sample AP Calc questions, and my complete AP Calc study guide over at my website, apcalcprep.com. Have a great one.